Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. It's my pleasure to invite Professor Shai Avidan from Tel Aviv University to give a talk here at MSR. Shai did his PhD in the Hebrew University in Computer Vision, was a postdoc in Microsoft Research Redmond, and since then been a researcher in Mitsubishi Electronics Research Lab and a senior researcher at Adobe. So, Shai?
Thank you. Thanks for the introduction. Actually, Yael introduced me to the grad program at Jerusalem, so that's great being here. So I'm going to talk about a paper we had several months ago with Tali Dekel and Yael Moses at ECCV 2012. But I thought that before going into this paper, I'll just give a short pointer to a paper that I actually have with Simon Coleman, who's my grad student, who's an intern now at MSR, and it's about template matching. So I'll give a 5-minute trailer to this work that will be presented next week at CVPR, and then I'll go to the main talk on photo sequencing. So fast match is a paper about fast affine template matching. It's a joint work with Gilad Tzur and Danny Reichman from the Weizmann Institute. And what we're trying to solve there is template matching. So given a template, you want to detect its location in the image. And what you see in magenta is the location we found out. And in green, it's barely noticeable, is the ground truth location. And you want to do it quickly and efficiently. And you want to have some global guarantees on the accuracy of the solution that you find. In fact, we can do it even on a smaller template. You want to detect this template over there, and you see that we got almost perfect result. You can barely see the green ground truth rectangle. And we can even deal with something like this. We can detect the whisks of the cat and detect the location in the image. And the code is up on the web. You're more than welcome to go download and play with it. We'd love to hear comments and feedback. And just a couple of slides on how this works. So we thought long and hard on how to solve the problem. And this is the algorithm we came up with. All you have to do is sample the space of all 2D affine transformations, evaluate each one of them, and return the best. And all the paper does really is formally prove why this is the right thing to do, and a lot of experiments to validate that the assumptions that we're making hold in practice. So the idea is as follows. Let's say that this is the transformation space. Assume that the x-axis, this is a 1D case, is the transformation space, and the y-axis is the error of each transformation. Okay? So when we say at step 1, take a sample of the affine transformation, we evaluate the transformation at each of these locations. These are the values that we have. And when we return the best result, we might return something like this, because this would be the sample transformation with the lowest error. Now, the key observation that we make, and that's something that is well known, is that we assume that images are piecewise smooth. Now, what this means is that if you take a transformation and slightly perturb it, the error that you'll get will change only slightly because the image is piecewise smooth. So most of the pixels of the template will land on pixels with similar values, and only around the edges there will be a change. This means that transformations that are not on the net, not on the grid like this one, which is the optimal one, cannot be too far away from the samples that we do have. So we have a way of formally connecting the error that you want to introduce, which in the template matching, to the sampling rate that you need to do in the 2D affine space. And within a matter of 2 to 15, 20 seconds, you get the results that I've shown you. So here are a couple of additional examples. In this case, the templates are 45% of the original image size. And you can see that this is the result that we get. This is the ground truth. So it's barely, you can barely see any difference between the two. Here are more examples. Template size is 35%, and it goes down to even lower than that. Now, in all these cases, we did it. This is a controlled experiment because we took the image, extracted the template, and then tried to find it back in the image. You might say there might be noise. So how will it work with real scenarios in which you have a template in one image and you want to match it to another image? So we used the Mikolajczyk data set. And what we are showing here is this is the template that we're using. And this is the location that we found in each of the successive 5 images. These are different images. You can relate this template to each of the other images through the homographies that they supply. And again, you see that we're doing a pretty good job. This is the worst case. We're detecting a 2D affine transformation. In this case, there is a projective transformation that you need. Therefore, we don't get the exact match. Here is another example. It's fairly challenging. There is a lot of repetitive texture, and still we do a fairly good job, except for the last case here, where we fail, and it's mainly because of the projective nature of the transformation in this case. We deal with blur. This is the original image. These are the 5 successive examples with increasing amount of blur, and we correctly detect the template in each of those. This is the bark sequence. It's a zoom plus rotation. And you see that we get fairly good results except for this one, but we can detect the template even in these 2 cases. And when we fail here, the failure means that we found this region such that the absolute error of this template is within a constant from the true global position. JPEG artifacts are no problem. And we did the same thing with the Zurich building data set. Again, there is a template here, and we find it in another image of the same building. And there are many more examples. So again, if you find this interesting, by all means, go either to my website or to Simon's website and follow the link to the paper and download the code and play with that. Questions?
How do you differentiate your algorithm with affine shift? Affine shift.
Of ASIFT, yeah. So ASIFT assumes that you can detect and describe interest points. So in many of the examples I've shown you, like at the beginning, it's not clear you'll find interest points on something like this. So all the feature-based methods will not work in this case. On the other hand, you might use our method and use direct methods to improve the result if you think you need a sub-pixel accuracy, because our system is pixel-wise accuracy. So in the paper, we give an analysis and comparison both to ASIFT and to direct methods and show the advantages of what we're doing. OK, good. So now back to the topic of today's talk, and that's photo sequencing. And this is the problem that we want to solve. Actually, that's an illustration of what we want to solve. That's a picture taken in 2005 of the announcement of the new Pope. And that's a picture taken from the same location 8 years later when they announced the new Pope. And right, so there is a new type of camera. You might call it a crowd cam. And it's a collocation of cameras in space and time. And the question is, what do you do with that? And there are a couple of interesting things to point out. For the first time, you don't have a single photographer who determines what's the right time to capture something. Everyone is capturing the image whenever they want. And you hope that they will capture it at roughly the same time when there is an important event going on, but there is no guarantee. And the second thing is that currently these images do not interact with each other. we do know that camera arrays are very useful to do a variety of things. You can get a huge panoramas, high dynamic range, do better tracking, whatever. But all the camera arrays I'm familiar with assume there is one person, usually a PhD student or his advisor, who carefully calibrated and synchronized the camera array in order to capture the high quality image. And the question is, can you work with such a noisy data set? So that's the goal of our work, to make a baby step in this direction of analyzing dynamic content from a collection of still images. So let's try and define it more formally. This is the park next to Tel Aviv University, and if you go there on a sunny day, you can take a picture of the boats on the river, and other people will take photos of the same event, and before you know it, you have a folder full of images taken at roughly the same time, from roughly the same location, and the question is, now what? How are you going to make sense of this information? So one obvious thing to try is try and place the images one after the other and play the video. And if you place them in a random order, you get a very messy result. It's very difficult to understand what's going on here, right? You can't infer the course of each boat. You don't exactly understand the dynamics of the scene. If you run our algorithm instead, you can see that how the green boat moves, how the white boat moves, and so on and so forth. So our goal is to take a folder full of images and try to infer the correct temporal order the images were taking. So that's the formal definition. Given n still images, determine their temporal order. And just to give you a sense of the dimensionality of the space, given you have n factorial possible permutations, and if you have 15 images like the example I've shown you now, the space is 10 to the 12. So you need to pick the correct order out of 10 to the 12 possibilities. So now that you know what photosequencing is, let me explain what it is not. The first thing to notice is that it's not video synchronization. And it's not video synchronization because you have very discrete and small number of samples from each camera. So you don't have the full video, which is a very dense sampling in time. You just have one or few images from each camera. And you need that information to recover the relative temporal order between images and cameras. The second thing that photosequencing is not is it's not phototourism, because phototourism deals with the static aspect of the problem. So you want to recover the camera position and the 3D structure of the scene. You don't treat the dynamic content of the scene. And the last thing is there was a very nice paper by Schindler et al. From Georgia Tech back in CVPR 2007. What they did there, they had images of Atlanta captured over a period of about 100 years. And they wanted to find the correct order because they didn't have the time stamp for each of those images. They used completely different techniques and the setup was different. We are interested in images that are captured in similar space and time and want to organize them. So we're using completely different tools. So the assumption we're making is that the images are taken from roughly the same location at roughly the same time, and we want to organize them. And the way we go about it, we take a geometric approach to solve the problem, and we detect and match feature points. Here are an example of feature points detected in one of the images. And then we use standard tools from geometry to find the fundamental matrix and the static features in the images, and all the outliers are considered the dynamic features. Okay, so we have the fundamental matrix between every image and a reference image, and we have all the dynamic features over there. So let's look at the dynamic features. This is the tool that we're going to use to solve the problem. And let's look at the dynamic features in this image. You see that in this particular image, the SIF descriptor, I think, detected all the points on the boat, but it failed to detect them on the boat up there. So you see, we're dealing with a noisy process, and for this particular feature point, it was detected in all these images that you see the red arrow. So in a subset of the images, this dynamic feature was detected and matched. For a different dynamic feature, like the one marked with yellow over there, you get a different subset of images. Okay, so the question is, how do you aggregate? There are two things. How do you take advantage of the images that you have the feature point? How do you use that to recover the temporal order of the images in the yellow subset or the red subset? And then how do you aggregate everything together into a global order of the images? So the algorithm consists of two steps. The first one is finding the partial order from each dynamic feature. So for the red dynamic feature, you get a partial order like this. For the yellow, you get some partial order like that. And once you have all these partial orders, you want to aggregate everything together and get one globally consistent temporal order for all the images. And I'll spend the bulk of my talk on the first part, and then I'll mention how we solve the second part. And the tool you're using here is something called rank aggregation. I'll explain more about it later. Questions? OK, so we want to recover the temporal order from a single feature set. And here is a plot to explain what's going on. You have the 3D point, and we assume it's moving along a straight line. And as it's moving along a straight line, it is captured by image 3, and then by image 2, and then by image 4, and then by image 1. So there is this implicit assumption that the point moves along a straight line. And moreover, it doesn't go back and forth. It's going in one direction. We don't care about the speed in which it moves. So one way to solve the problem is to say, well, the order of the point in 3D implies the temporal order. So what we can do is, if we knew the positions of all the cameras, we can reconstruct the line and then intersect each of the rays with the line, get the position of the point along the 3D line, and solve the problem. And theory tells us that 5 cameras are enough to recover the 3D line, and then you can recover the position of the points and get the temporal order. We want to avoid that for 2 reasons. The first one is you make strong assumptions about the data, in the sense that you need all the cameras to be in the same coordinate system. So you need to run bundle adjustment, which is a step above the fundamental matrix estimation that we're doing. The second thing is a little more delicate. We actually don't care about the 3D structure of the scene. At this point, all we care about is the order of the images. And therefore, when you're trying to do this reconstruction, you might be more sensitive to errors and noise. So we did some synthetic experiments to validate that, but that's not the point. We really wanted to avoid the 3D reconstruction because we just care about the temporal order of the images. So instead of working in 3D, what we want to do is work in 2D. And that's fairly simple. All you have to do is project this trajectory line onto the image plane here. And the 3D points are projected to points along this line. And you can do the entire analysis in the image plane. Okay, so we're moving from 3D to 2D. So in order to do that, we have to make an assumption. And we're making something called the static image pair assumption. We are assuming that there are 2 images that are taken by the same camera, and this camera is static for that time period. Okay, so let's denote them I1 and I2. And how is this going to help us? Well, let's see an illustration here. So this is the first image taken by the reference camera, and this is the dynamic feature point that we detected. And now we take the second image with the same static camera, and let's say the boat moved here. So now, because we have the static image pair assumption, we can pass a line connecting these 2 points. And this is the projection of the 3D trajectory of the boat onto the reference image plane. Okay, that's the crucial thing. We made our life very easy because we assume we had one static camera taking 2 images at different time steps. It can move afterwards, but that's the assumption we're making for now. So now that we have this line, let's see what happens when we take a different image, IK, and we detect the same dynamic feature on the boat. Because we have the fundamental matrix connecting IK and I1, we can compute the epipolar line, take the intersection between the epipolar line and the trajectory, the projection of the trajectory, and get the position of this dynamic feature as it would have been seen at time tk in the reference camera system. Okay? So now we see that the temporal order of the images is I1 and I2. That's the two images coming from the reference camera. And we see that IK was taken before them. And you can do that for each of the other images, and you'll get a temporal order out of the 2D analysis that you're doing in the image plane. Okay? So all these feature points, so this feature point was seen by 5 images. That's the temporal order we get here.
So, a couple of things. Obviously, the reverse order is just as valid, which I assume you're just putting both of those into your hypotheses.
We assume that we have 2 images from the reference camera, and we assume we know the order of them.
So you have 2 from the same camera? Okay.
Yeah.
Got it. All right. And you know the time, the relative times.
Yeah.
And then the other one, obviously, is that you're not crossing the line of action, so to speak. Cameras are
Yeah. So this plays to the assumption that images are taken at roughly the same time. So a point doesn't have to go back and forth. We assume it's going only in one direction. If it's oscillating, then we have a problem, and I'll show an example later on dealing with that. One nice thing to observe here, and it goes to the fact that we don't do 3D reconstruction. I'm talking all the time about points moving along a straight line. In fact, we know what is the path of this boat. You see it from the trail it's leaving behind, and you see it's not a straight line. But the algorithm is robust enough, and the assumption, because all we care about is the temporal order, is robust enough to give us the correct order, even though the objects do not move along a straight line. And another point that I would like to make is that each feature point can move along a different 3D line in a different direction. They don't have all to move in the same direction. That's not necessary. Yeah, it doesn't matter. If you can approximate its motion by a straight line, so depends how curved is the actual trajectory. As long as the order of points do not flip when you project it on the line, you'll get the correct order.
I guess what I was referring to is, if some cameras, there's a line of action, right? And if you go to the other side.
Oh, yeah.
Right? In one case, they're going from left to right. In the other case, they're simply going from
It doesn't matter. It doesn't matter in the sense, it would matter for this feature point, yeah. But if you have, so what will work if you had one dynamic object moving in this direction and another dynamic object moving in this direction? That will be fine. Looking from both sides of the action line will be a problem. Yeah, we have example of similar nature later in the presentation. I'll mention that. Okay, so there are a couple of limitations with this approach. The first one is you have this reference image, which means that you need to match all feature points and all images to the reference image. So it limits the amount of images you can work with. And the second problem is that you're not making use of all the information that you'll have, and I'll show an example in a minute. So here is an example of a parade in Tel Aviv. Let's say this is your reference image. It would be extremely difficult to match this image and this image to the reference image. The background is way too different, even though the dynamic object that is the focus of our work is fairly prominent. So we would like to alleviate this problem somehow. The other problem is that usually people take more than one picture with their camera, and we are not taking advantage of the fact that we know the temporal order of images within a camera. We don't know the exact time step, but we know that image 2 was taken after image 1 and before image 3 and so on. So we want to make the approach more scalable by removing the reference image assumption, and we want to make the approach more realistic by looking at multiple images that you know the temporal order in each of the cameras. So let's go back to our illustration. We don't have the 3D trajectory line anymore, and all we have are the projection of this dynamic feature point in the image plane. Okay? So let's take this as the reference image, and we'll do it for each of the images as the reference image repeatedly. And you can map the feature points, the points, to epipolar lines. So what you have in a particular image is a point, and let's say 3 epipolar lines coming from the remaining 3 cameras, right? So here is another, this is a zoom in just on the image plane of a particular camera. This is the projection of the dynamic feature point, and these are the epipolar lines corresponding to the projection of this dynamic point from different time steps on the image plane of this reference camera. So if we had the trajectory, the projection of the trajectory, then the problem is solved. But we don't have. So this might be the projection of the trajectory, this line here. Or it can be this line here. So how are we going to solve this problem? So one thing to notice is that if you take this line and perturb it slightly, the order of the points will not change. So the question is, when will they change? So there are two types of cases in which it will change. The first one is fairly simple. If you pass, the trajectory line must pass through this point. So we need to establish another point, and we'll take the point to be the intersection of these two lines, for instance. So you'll notice that if you have a trajectory line to the right of this line, then the order is green, then red, or red, then green, depending on the direction in which you're looking at. And if this black line crosses this critical line, then the order of points changes. This is green, red, and now it switches to red, then green. So this is one type of critical lines. Every time the trajectory line crosses the critical line, the order of points along the trajectory changes. There is another instance, and the second type of critical lines is critical line that is parallel to each of the epipolar line, but passing through the feature point here. So to see why this is true, if you have this as a line, then you have blue and then green. And if you cross this critical line, you have green, then blue. Okay? So taken together, we've removed the temporal assumption. We don't have the static image per assumption, and therefore increased dramatically the number of possible permutations that a single dynamic feature can induce. In fact, if you look at the image plane, it's now divided by all those critical lines into regions. And it's pretty obvious to agree that within each region you have just one order, well, actually two up to the direction of the points, which infers the order of the images. So here is a quiz. Let's say you have 15 images. What's the maximum number of permutations? And let me remind you that n factorial equals 10 to the 12 possible permutations. So if I'm giving you this number, how many different permutations will you get from the analysis I've just shown you? Is the question clear?
Yeah. Is it independent number of points?
Yeah. So let's see. So the number of permutations is 2 times the number of regions, because for each region it can either go back or forward or backward. And the number of intersection points for the first type of critical points is n-1 choose 2. And for the parallel lines, the second type of critical lines, it's n-1. And if you do the computation, you end up having 210 possible permutations. Okay? So that's in the case of n equals 15. That's the maximum number of permutations. In practice, you can do much better. And this is an example showing that. What we see here is a point. This is the dynamic feature point. And you see here all the epipolar lines from the remaining images in the data set. And there are 2 cameras. And we know the order of each of the images in each camera. This is one particular order. This is the particular order of images from the other camera. So now that you evaluate all these 210 different regions, for each one, you see if it violates any of these assumptions. And if it does, you throw it away. You know it's not a possible solution. In practice, we get about 4 or 5 different permutations for each dynamic feature. So we've replaced the static image per assumption, and we get a much, but we still get a very small number of permutations per dynamic feature. Okay? So to recap what I've shown you so far, we're using geometry and geometric reasoning to infer the temporal order for each dynamic feature. You can either do 3D reconstruction, you can do the solution based on the static image pair, or you can use these temporal constraints that I've shown you a minute ago. In any case, each dynamic feature will give you one or a few number of temporal orders on the image set. The second question that we need to solve is how to aggregate all the information into one consistently and global order of all the images. So the way to solve that is to think of the problem as a graph. Each node is an image. And let's say that this is the correct temporal order of the images, then you'll have the edges like this. I3 goes to I1, to 4, 5, and 2. Now, if we were lucky and there was one dynamic feature that appeared in all images, let's say this red point, and there were no errors, we'll get that, and then it's just topological sort on the graph. We get the solution, it's trivial. In practice, that's not what we have. What we have is a partial order from the green point, another partial order from the blue point, and another partial order from the red point. Now, the problem is that there might be errors. And the way errors are manifested in this graph is that there might be a cycle. If you look at the edges, you'll see that there is a cycle between 2, 1, and 4. And that's impossible. Okay, so the question is, how do you aggregate the information and resolve this conflict? And the way to solve it is through a tool called rank aggregation. And you define a metric on the space of all possible permutation. And essentially, you take two permutations, and the distance between them is the number of pairs on which they don't agree the order. Okay? So we're looking for a consensus full order sigma that is as consistent as possible with each of the partial orders sigma I. So each dynamic feature voted for one or a few temporal order sigma I, and now we're looking for one global temporal order sigma. Yeah? This problem has been investigated extensively in social studies. This is how you do voting. And in the context of computer science, we are following a work by Dwork et al. From 2001. And what they had is the following problem. They had a search query problem. You want to do, you run a query, and you get results from multiple search engines. So now you have the pages ranked by each search engine separately, and you want to aggregate all the ranking into one global consistent ranking. And the solution is based on Markov chain solution. Markov chain approximation, the problem in general is known to be NP-hard. So how is the solution going to work? We construct the transition matrix. We build the graph and we construct the edges such that the weight of this edge is the probability that image 1 appeared before image 4. You can simply count the number of features that voted I1 before I4. And that would be the probability of, that would be the weight of the edge ij. And now you can look at the transition matrix that is associated with this graph, and you do a Markov chain. Essentially, you initialize the state, the probability that the last state is each of the images to be a uniform distribution, so it's 1/5. And if you look at the leading eigenvector of this transition matrix M, you'll get that it's 1 on the last state and 0 everywhere else. Imagine a random walk. As you take it to infinity, with probability 1, it will end with at the last position. So you can place image 2 there, it's the last image, remove it, and repeat. So that's the whole algorithm. What happens in case you have a conflict meaning you have a cycle? In that case, when you look at the eigenvector, it will not be all zeros and just 1. It will be something like this. Let's say there is a cycle, so all elements outside the cycle will be 0. But within the cycle, there will be some values, and you're not guaranteed that the correct image within the cycle will have the highest probability. Let's say that this image got 68% probability, so we'll choose that to be the last image, but it might have been this one or this one. And that's the approximation nature of the algorithm. That's why we can guarantee the globally optimal solution. Results. So the first question people ask us is, why bother with this approach to begin with? Why can't you just use the clocks on the cell phones? And I thank you for not asking it until now. So we ran an experiment. We played a stopwatch on the screen and asked all the students in class to take a picture when it reaches 10 seconds and again when it reaches 20 seconds and send us the images. And this is the histogram of the times that you get. This is the time offset, and this is the number of people that took an image at this time offset. So there is a total of 40 images, I think, here. A couple of things to notice here. The range is about 6 seconds. So if you're talking about a dynamic event, 6 seconds can be, depending on the type of event, quite a lot. That's problem number one. Problem number two is it's not a unimodal distribution, I think, because there are there are more, I think, 2 or 3 types of carriers in Israel. Maybe each group of phones is clustered around a different peak. Moreover, there are a couple of outliers that I'm not showing here that they had their camera phones completely off sync. They were several minutes off. So given all these reasons, I think there is room for using a vision-based technology to properly synchronize images. Here are some results. Here are 9 images taken, I think, by 2 cameras. In this case, we're using the static image pair assumption. These are the 2 images that are taken by the static camera. And these are results in random order. It's not very clear what this guy is doing. And that's not me, by the way. And this is the result you get. Okay, I'm playing it back and forth. So you can clearly see that he's skating from left to right. Here is another example, the same setup. In this case, look at the little girl on the slide. You'll see it's her location. That will give you an indication of how well we're doing it. Okay, and again. So we're recovering the correct temporal order here. And another example, this is a challenging example because if you look at the image, the top third is blue sky, there are no features there. The bottom third is reflections of the water, so it's difficult to get any feature points. So just getting the epipolar lines, the static feature points, and computing the fundamental matrix is not trivial. And another problem is that the motion of the girl is almost parallel to the epipolar lines, which makes the intersection that much more sensitive. So I think a 3D reconstruction here will not work very well, but in our case, you see that we get a fairly good result. Okay, a couple of experiments using the data courtesy of Park et al. From ECCV 10. We have here 5 cameras, and we have a number of images from each camera. So in this case, we're using this assumption. We're not using the static image pair assumption. The points were manually marked in the images. And going back to your comment earlier, actually the guy is climbing up and down. But because we only assume that the object is moving along a single direction, we clip the sequence only to the images going in one direction. Otherwise, it will be messed up. And you can see that it's constantly climbing up. Okay, and let me play that again. Good. And another example from the same paper. There are 14 images, 4 cameras, and we correctly recover the temporal order here. And the last example is from a parade. There are 3 cameras, 4 images, and 2 images respectively. And this is the result that you'll get. And again. Okay, so let me summarize what we've done. I think it's a cool problem. It's also, it focuses to think what are the assumptions that you want to make and play with geometry, which I personally like very much. Also, I haven't seen much work on rank aggregation in computer vision. I think it's a very powerful tool. There are many instances you can think of where you have ranks between partial ranks and you want to aggregate everything together. In the future, I think the main problem we had is the problem of matching. Detecting and matching feature points is extremely difficult. It works well for the static part, so SIFT or ASIFT will work fine. But for the dynamic feature points, first we couldn't get SIFT to detect feature points on the dynamic object. And even if we managed to do that, then the matching would fail because the descriptor is not working. You can't match the descriptor of the same dynamic point because especially on humans, they change their appearance too much for the matching to work well. So in this case, what we did, we used a code by the Adobe group, a non-rigid dense correspondence that computes a dense flow field between two images, and it seemed to work better for our problem. As a follow-up to matching, this will allow us scalability. Ideally, you want to work with hundreds or thousands of images, and if you have automatic matching, then you can scale really well. And there are probably new applications, for instance, separating the dynamic from the static objects in the scene to highlight if something really changed or not. That's it. Thank you very much. Oh. Yeah.
So I have a question. You do basically aggregate voting and you find the majority vote, but we know that time has one way of progressing, and it's enough that you have one good vote. I'll give an example. Suppose you have a scene where a lot of objects are having a periodical motion, let's say between 2 points, and one or few objects that have a linear motion around. Looking at that, you know that this is not a repeat.
Yeah.
But
so I'm not going into that in the talk, but in the paper we did some trying to figure out the confidence that each dynamic feature has. So we might say this dynamic feature appeared in more images, therefore we trust it more. You can add all these priors into the voting process. So if you have a dynamic feature that you're very confident in, then it can have a higher vote, and this will completely dominate the solution, and then you'll get the trivial solution. So there is a way to introduce these priors into the framework. The rank aggregation is agnostic to all this. It just takes a matrix that tells you the probability of I occurring before J and gives out the solution. Yeah.
When you're not using any time information from the camera, why doesn't the vote go backwards? Is it not equally plausible?
Yeah. So in this case, we manually selected out of the two possible solutions, the solution which the vote is going forward. But you're completely right. In the first case, when you had a static image pair assumption, then because you know the order of the two images from the static camera, it determines the sign bit of time. Yeah.
You said you you determined the probability that one image happened before the other based on the number of matched features, right? Did you try any other things like the quality of the features or any like geometric assumptions?
I don't think we did. You can think of the quality of the match. I think that would be one option. But in practice, that was never really the problem. We also did synthetic experiments where we used 200 or 300 cameras or images, if you will, and we introduced errors. And rank aggregation gave a solution that was like 98% accurate. The real problem is getting the matching. That's the killer problem.
These are relatively controlled scenarios. Did you try it on in the wild?
Yeah, the carnival is as wild as we could put our hands on. It's difficult because the background changes dramatically. You think that it's when you look at the images, then you see that the background changed quite a bit, and there are lots of motion. So just getting the feature points there is difficult. Yeah.
Have you tried applying that to a sports scene like, say, football? Like, assuming that, say, the team is moving forward, so that you have your linear motion, but you still have players with similar jerseys and stuff. I would assume that the matching would be problematic.
I agree. I wish we don't have the data set for that. if we can get enough data, we would love to try our algorithm on that. Thank you.